So I guess I'd like to begin by thanking Ben and his wife Catherine for organizing this. I know it's an awful lot of effort on their part, and I know all the speakers are grateful to have the chance to speak. In addition, I'd also like to thank each of you for coming, because when scientists travel to meetings, professors, usually it's paid by the state, and they get to go to all these great places, and somebody else is paying for it. But when you guys come to this meeting, you're paying out of your own pocket. And that's quite a testament, actually. So I wanted to mention to you guys how much I've enjoyed when I come to these meetings to get to meet each and every one of you. And I think there's something really beautiful of humanity. Even though we have all different ideas and so on, I almost relish in every human being that I meet. So thank you for giving me that gift. Now, I'm going to speak about the life cycle of the stars, and for those who are interested, I gave a talk. It was a very brief talk at the American Physical Society meeting in Salt Lake City, Utah last spring. And if you go and look at that for that talk, you'll also see some of the slides. They're still there uploaded, so you can see what I said last spring. Now, if those of you who might know me personally know that I just am crazy about my grandchildren. So I think it's one of the great gifts in life that we get to grow old and we get to play with our grandchildren. So I can't tell you enough how much I've enjoyed it. Of course, since they can't enter into my world, I always enter into theirs. So I'm always on the floor playing with my grandkids when I do get the chance to see them. And this talk is dedicated to all of them, both the ones that I have now, one that's on the way, and others to come. Now, of course, if you followed my work, you know that I've talked about the sun, and that I've mentioned that it's metallic hydrogen in structure, that it has a true lattice. And this actually has consequences for the stars. And now that I've had a pretty clear exposition of the sun, I want to bring some of these ideas to the stars. And I've been working on this for a few years now. And that's part of the reason I didn't go to the EU last year, because I didn't really have a talk ready. And I don't like just giving a talk for the sake of giving one. And so I deferred. So for those who might have interpretations as to why I wasn't at the EU last year, that's the reason. And also I wanted to be with my grandkids. So if you look at the stars, we have the HR diagram, where we look at the luminosity of the stars, and we can plot the stars on a 2D plot like this. And what you observe is that they kind of arrange themselves in groups. And on the lower scale there, you see the different spectral classes of the stars, and that's related to their color. And also they infer their effective temperature. And on the vertical scale, you're looking at the luminosity of the stars, how bright these stars are. So the higher they are on the scale, more to the upper left-hand corner of the diagram, the brighter the stars are. And they are arranged in groups that have been named, and we're going to discuss these groups one at a time here today. And so I've just put a few representative stars in these groups. Of course, in the main sequence, there are many, many more stars, and there's the asymmetric branch that's there. So there's many, many more stars in this, but this is just a representation for this talk. So it's well known that the sun is the Rosetta Stone of astronomy, and as the most proximal star to the Earth, the sun provides us with the best opportunities to study the physics and chemistry associated with the stars. And I should tell you that when I give a talk, I usually tend to give what I want to say on my slides. People find it annoying because I put a lot of writing on my slides. But that way you do get to follow along and I don't miss any points. So the analysis of the sun not only guides theories relative to our local stars, but it serves as a basis for understanding all stellar objects. So as a result, any change in the accepted solar theory has consequences throughout astronomy. So a new perspective relative to the stars can be formulated based on the existence of a lattice structure in the stars. So not only am I saying that all the stars are hydrogen, but but they all have, they're all a manifestation of their existing or poor lattice structure. So I always like to remind people, but scientists are they really care about their ideas and stuff. And we have to remember that all of us are fallible, and we have to remain open to the concept that prevailing ideas can be improved upon. But I especially like this one, that change brings hopes to our children that they too can contribute to the advancement of science. So when we're here on this planet, we have to remember this next generation, and that we want them to come up with good new ideas too. So we're going to talk about the Standard Model just a little bit. So the sun is currently viewed as a gaseous plasma, which can be treated mathematically as a fully compressible gas. This leads to the concept of black holes as massive stars collapse on themselves. And if you reverse these mathematics, it helps to account for how a point mass could result in Big Bang creation. So these things are inherently linked. If you permit the sun to collapse on itself, the Big Bang creationists want this kind of behavior. And of course, I reject that the sun will ever collapse on itself. So here's a figure of the Standard Model of the sun, of a fully gaseous sun. And we have different zones in them. So at the center we have a core, and then in the gaseous model they believe that there's a radiative zone here where photons are traveling through this zone. And then there's a convective layer, convective zone. And these are all at high temperatures. The core is at 15 or 16 million degrees. And then by the time you get to just below the photosphere, they say it's about 2 million degrees. And then the photosphere is a very, very thin layer, and they're saying it's only 6,000 degrees. And then above that, we have the chromosphere, which is at times slightly lower in temperature than the photosphere. And then out in the corona, they're proposing these unbelievable temperatures, which of course I've disagreed with, and I won't restate it later in the talk, but just now, they're saying these temperatures are real, and I'm saying they're actually a product of electron affinity, and the electrons are being stripped from atoms in the corona, and that's why we have ions with very high oxidation states. Now, in the Standard Model, we have three forces that are working to stabilize the sun. So stellar stability in the Standard Model is governed by hydrostatic equilibrium, which is established between internally directed gravitational forces and externally directed pressure, for instance, electron gas pressure and radiative pressure. Gas pressure is thought to dominate in a star like the sun, while radiative pressure is believed to dominate in supermassive stars. Well, the problem I have is that gas pressure, and I've mentioned this before, requires a real surface, but none exists inside a gaseous sun. So just think of a billiard table, and of course gas pressure is what holds up the Earth's atmosphere. So what happens is, if you have an atom that's a molecule or an atom that's coming and it hits the surface of the Earth, it gets bounced back up, and that holds up the atmosphere of the Earth. So to have gas pressure, you need this surface. And you could think about this if you play billiards. If you hit the bank, that's like a surface, the billiard ball will come off of it. The cue ball will come off the bank. But if you hit another ball, the cue ball can stay stationary and transfer all that momentum to another ball. So you absolutely require, when you discuss force, gas pressure is always force over an area. So if you don't have a surface, you can't have gas pressure. And, when you look at how the astronomers deal with this, they say, well, this is from Clayton's book, and Clayton this is a standard textbook in astrophysics. It's an old textbook, but it's still today a reference book. And Clayton talks about this. He says the reflection or absorption of these particles from a real or imagined surface in the gas results in the transfer of momentum to that surface. Of course, you can't transfer momentum to an imaginary surface. So it doesn't make any sense. So you can't have gas pressure in the sun, and that's one of the reasons why the gas model cannot survive. The other reason is that they're arguing that photons are produced deep in the interior of the sun, and over a process of hundreds of thousands of years, slowly move out to the level of the photosphere, where they finally escape. In doing so, theory involves that Kirchhoff's law remains valid at every internal layer, each of which remains in thermal equilibrium. The sun acts as a slowly leaking sieve of photons as it dissipates heat to its surroundings. So the problem with these ideas is that objects reach internal thermal equilibrium with conduction and convection. Radiative emission is utilized to achieve thermal equilibrium with the surroundings. So you shouldn't even have photons internal to the sun. So I have a problem with both mechanisms to sustain a gaseous sun. And then also, they argue that in the gas model, that radiative heat transfer, while present in the sun, becomes much more important in larger stars. And then they also say that there's no meaningful heat conduction in ordinary stellar matter, but only becomes important in degenerate objects. Okay? So I completely disagree with this. We have to have heat conduction in the sun. And they try to say that conduction cannot take place in the photosphere. No, I say you can't have conduction in the photosphere according to them because, of course, their density is too low at 10 to the minus 7 grams per centimeter cubed. That's a vacuum. Then the other problem with the gaseous model is their energy production, and they link this to stellar evolution way back at the beginning of understanding energy production with nuclear reactions. So they say that energy production in the sun is linked solely to the creation of helium. So in this modern theory, our sun has been crippled. It can make none of the heavier elements. And this is vital to preserving our current understanding of stellar evolution, as the primary driving forces for changing star types is currently by switching nuclear reactions. So I disagree with this. I mean, this is just, we have no evidence that these nuclear reactions, what nuclear reactions are actually taking place in the stars. So how can you argue that they're switching? And then, of course, they say, well, it's a temperature thing, and we know these temperatures from the laboratory and what's required and all that, but they have no idea what the internal behavior of a star can be like. So they also argue that all heavier elements in the sun had to be generated by a first-generation star, which exploded, and then for which signs of existence are no longer detectable. But if I'm correct that if the sun can make all the elements, then what causes stars to be different from one another, if not driven by different nuclear reactions? So you can see, even if you go back to 1938, when Gamow first discussed energy sources in the stars, he linked it immediately to stellar evolution. So this was always linked. You know, they had no other way. They weren't a gaseous model, so they had no way of making the stars evolve. So that's why, you know, they spent tons of time trying to argue that nuclear changes in nuclear processes were responsible for the evolution of the stars. And the classic paper, of course, is by Burbridge and his wife, Fowler, and Hoyle. Fowler, of course, is a Nobel Prize winner. So according to the standard model of the sun, the energy production in the sun is by the pp chain and its branches. But the first reaction in this process has never been observed on Earth. And the reaction in the bottom left is two helium isotopes that come together to make helium-4 and two protons, and that's said to dominate at solar temperatures. Now, in addition to that, Hans Bethe initially believed that the sun was about 10% hydrogen, and he along with the Weizsäcker, you have to excuse my German, I don't know how to exactly pronounce it. They came up with the CNO cycle, and so the cycle is not now thought to play only a minor role in the sun, but becomes important in larger stellar masses, like more than 1.3 solar masses. And there are many branches, some of which are said to be occurring only in massive stars or under high temperature and pressure, that occurs in nova and X-ray bursts. So they proposed this cycle, okay? And the problem with this, Bethe was German, and the problem with this such a cycle is cycles have to be regulated. Now, just before the CNO cycle was proposed, another German, Hans Krebs, discovered the TCA cycle. Now, for those who know me, you know that I have a lot of training in biochemistry. And, when the TCA cycle was discovered in 1937, this is before the CNO cycle by about 2 years. Of course, we didn't know how it was regulated. All we knew is that, we had these intermediates and we're just going from one to another, and we thought everything was hunky-dory. But as science progressed, then we discovered that the TCA cycle is actually very highly regulated. We have allosteric effectors of enzymes, feedback inhibition of reactions, genetic expression of proteins, and oxygen availability. In addition to that, there's anaplerotic reactions, like that catalyzed by pyruvate carboxylase in the upper left, which constantly help maintain an appropriate level of intermediates. Okay? So we have a cycle in biochemistry, and the reason it exists is that all these intermediates are regulated and controlled to make sure that this cycle keeps running. Okay? But such a mechanism are completely unavailable to the stars, and that's why the CNO cycle can have no practical viability as an energy source. It's what we've done is we've taken a bunch of reactions and we said, well, look, we can make these together and make a cycle. Well, you can do that on a piece of paper, but to say that it actually occurs in nature, that's a different thing. Now, if you look at stellar evolution in the Standard Model, they come up with some really interesting ideas. They say that stars were born by the gravitational collapse of a gaseous cloud, but the rule in the laboratory is that gases expand to fill the void. And also, as they age, stars like the Sun become increasingly hot, change their fusion reaction to helium burning, and move towards the red giant branch. So you're following the white line here. Then they adopt carbon burning reaction, rapidly cross the main sequence, and become white dwarfs. In order to move to higher fusion reactions, stars must have a higher initial mass, starting mass, and reach incredible densities. So that's what the current models are saying. So if you look at the fusion stages for a star with 25 solar masses, you see that you initially burn hydrogen for about 7 million years, and then you convert to helium and so on. And as you convert to each substrate, each fuel that you're burning, the duration here, which you see on the right, comes down lower and lower. But the other thing that's happening is the densities and temperatures are going through the roof. So I disagree with all of it. These densities and temperatures don't exist. So let's talk about now the liquid metallic hydrogen model. Just a brief review. So I think that we've really missed something when we've ignored that condensed matter exists in astronomy beyond the planets. So the assembly of hydrogen into condensed matter, clusters, liquids, and solids drives the formation of the stars, their appearance, and their life cycle. And there are many observational features that can be explained by introducing condensed matter and the existence of lattice structure into the field of astronomy. So you can have hydrogen clusters and star formation. You can have emission lines to explain Wolf-Rayet stars from a poorly formed lattice. I'm going to go through these. The violence exhibited by luminous blue variables is the initiation of lattice structure. The occurrence of supernovas and red giants, rapid or gradual exfoliative events. The lowered luminosity of white dwarfs is an alternative lattice structure. Spectroscopic binaries and variables, simultaneous and alternative presence of differing lattices. The emission lines in the chromosphere, I've discussed that in previous talks. They constitute evidence of condensation reactions, and emission lines in the corona, they are evidence of electron affinity and condensed matter in the corona. So I've said this repeatedly. The sun is condensed matter and has a true surface. So if you talk to an astronomer, they always tell you well, the surface of the sun is an optical illusion. Of course, as Americans, we should be highly upset with that because we're spending millions of dollars right now building a brand new solar observatory in Hawaii, and obviously we don't want to look at just illusions. So we are looking at something real, and that's why we're building these telescopes. So we must, and when I talk about, when they say, well, look, it's an imaginary surface, they say, well, look, there's an opacity change at the level of the photosphere, and that's what causes the surface to become apparent. But actually, the problem is that it doesn't happen just in the optical. At every frequency, the sun is telling us, I have a real surface, okay? This is true at very low frequencies when you do helioseismology, and it's also true in X-ray. When you look at emission lines in the solar atmosphere in X-ray, the line intensity doubles when you cross the photospheric surface. This is explained in previous papers of mine. So it's over all frequencies, and that's all the information you could ever have to say that something has a true surface. Of course, somebody was reminding me today that Doppler images of the sun that show transverse waves with the flare and the ripples on the sun, they really enjoyed that. That was Martin, I think, that told me that this morning. So there's plenty of evidence that the sun has a real surface, and no other model can survive without putting a surface there. So solar emissivity must be explained by the use of an appropriate structural lattice. And I've always said, since I've been in this business crazily for the last many years, 15 years now, that the only proof that's really required to establish that the sun is condensed matter is the continuous solar spectrum. Of course, I've published a paper on 40 proofs, 40 lines of evidence for condensed matter. And if you want to understand why the solar spectrum is the only thing we need, you could look at stellar opacity, the Achilles heel of the gaseous sun. One second, I'll just take a little drink of water here. So in a condensed model of the stars, solar collapse is prevented by the use of condensed matter. And actually, Jeans realized this even in 1933. He said, any mathematical analysis shows that if the center of a star is either liquid or partially so, there's no danger of collapse. The liquid center provides a firm basis for the star as to render collapse impossible. And, you know, I've met all kinds of people here, and I'm sure some people have worked in hydraulics in their life, and you understand that liquids are incompressible or essentially incompressible. And that's why the sun cannot collapse if we make it condensed matter. And I've also tried to explain privately to people, well, how are we going to form a star then? And I want to form the star from condensed matter by using clusters. So we know that hydrogen clusters exist, and I believe that they're a good beginning for star formation. So we want to start by the simplest thing. We just have hydrogen at very low temperature, and the assembly of hydrogen into condensed matter drives the formation of stars again, as I mentioned at the beginning. And the body of the sun was built from condensed matter and remains condensed matter. Note that condensation reactions of this type must involve some means of dissipating heat. Otherwise, the temperature will rise. In the laboratory, heat dissipation can occur through conductive paths, but in vacuum, emission of electromagnetic energy or light must occur. So as hydrogen is condensing like this, we must have light emission. And there's positively charged clusters that have been known to exist since 1969, and here are a few references related to those. It should be noted that hydrogen clusters should be stable up to dust size because charge can stabilize the clusters against sublimation. So you have delocalized charge in the cluster, and that stabilizes it. Recently, we've just been able to synthesize negative hydrogen clusters with odd number hydrogens, and where you have one hydrogen that's negatively charged and is surrounded by a group of hydrogen molecules. And these had lifetimes of several milliseconds, and they were formed by permitting neutral hydrogen clusters to initially build within liquid helium droplets, and then by bombarding the resultant with electrons. So I want to start building the stars from something simple. And the reason is, and I know people want to use electric forces and so on, but before we do that, and this could be very important later on in the evolution of the stars, but the first stars, you can't put an electric field there yet because it doesn't exist. You have to have some means of generating it. So a hydrogen-based hexagonal lattice should provide much of the physical properties, should share much of the physical properties of a graphite lattice, not only in emission and potential electrical characteristics, because graphite is a semi-metal, but also relative to intercalation chemistry and exfoliative forces. So, because we know that graphite undergoes these processes. And of course, metallic hydrogen was first proposed in 1935, and when the paper initially proposed it, they were considering a body-centered cubic, and later on said, well, actually, you know, the hexagonal layered lattice of like graphite would be possible for metallic hydrogen, and that's the lattice that we want. And of course, recently somebody has synthesized the graphene, just a single layer of metallic hydrogen in graphene form that was done a couple years ago, and I presented that in a previous talk. But Neil Ashcroft, who's a very well-known condensed matter physicist, one of the leaders in the nation probably, and one of the world's expert on metallic hydrogen, I've quoted this before, he says that, you know, metallic hydrogen should be able to appear black like graphite and have the same properties as graphite in the optical. So when I talk about intercalation, I say that just like graphite, metallic hydrogen in a star will prevent all other types of atoms from residing in the intercalate region, in the hexagonal plane. So the only thing that can exist in the hexagonal plane must be hydrogen, and that's because you want the quantum condition to be preserved for conduction for the electrons. The electrons are delocalized in this plane, and since you want to preserve that quantum condition, any non-hydrogen atom will be kicked out, and then they end up resting in these intercalate regions. So this is known in graphite, and this is what I propose on the sun. And of course, these intercalate regions, the atoms that are intercalate atoms can't really move up and down here. They're restricted by the hexagonal planes, but they have freedom of motion. This is known in graphite. They have freedom of motion in their as long as they stay in their own plane. So in order to remain intact, the hexagonal planes of hydrogen act to exclude all other elements. This serves as a major driving force in accounting for solar activity, solar winds, and gradual or violent stellar reactions. When the sun is quiet, solar winds act to remove the intercalate atoms that exist between planes by ejection from the poles or coronal holes. With solar activity, helium and other elements are expelled from the equatorial regions of the interior into the corona and beyond. So what I'm saying is, why does the sun go active? The sun goes active because it wants to degas itself from these intercalate atoms. So this is a very reasonable mechanism to explain solar activity. You have, in the quiet times, the solar winds are coming from the poles, and things get degassed very nicely coming out of the poles, but you can't get rid of the atoms that are being built up in the equatorial region, and that's why the sun is going active, to get rid of these things, which is important to its stability. So stars. So now we're going to talk about stars and lattice structure. So what I've said is that, you know, all the stars, their primary building block is hydrogen. They can contain other elements, but always remember, well, you don't have to remember if you don't want to. We'll say, if you want to understand what I'm trying to say, that the stars, the primary driving force for making a star and keeping a star is the powerful forces of the lattice of hydrogen, okay? So I want hydrogen lattices in the stars, and the lattices can be different, but they have to exist, and hydrogen is the driving force, and the other elements are helping to create this hydrogen structure by helping in condensation. The position or absence of a star on the HR diagram is a direct manifestation of its lattice structure or lack thereof. So I say, well, where a star is going to appear on this diagram depends on the lattice that it has. Okay? How am I doing? All right. So now beyond the HR diagram, which is a luminosity and spectral type or temperature plot, there's also a mass luminosity relationship in the stars, and this was first reported observationally by Hertzsprung, which is the H in the HR diagram, and he plotted the relationship for the stars, the sun, and several known binaries where the masses could be accurately determined. So we know that for the main sequence of the stars, there is a mass-luminosity relationship. Now, a theoretical expression was advanced for this by Eddington, and it was done in 2 papers. They're each cited here with the little stars designating which paper is which equation. But you can forget about the equation. The thing that I want to highlight about these equations is that Dr. Eddington he's invoking things that can never be measured in his equation, right? So he wants like the stellar opacity constant. I mean, the kappa value for inside the star. Well, he's never going to know what stellar opacity is within a star, and I've said that there's no radiation within a star. So, you know, what does the constant mean? Then he also has this beta, which is the gas radiation pressure ratio. I mean, how could he know what is the amount of gas pressure or radiation pressure that is within a star? I mean, this is all conjecture. And then the other thing that he talks about is what's the average molecular weight of the species that makes up the star. Again, this is all conjecture. So if you want to have enough, you have 3 free parameters, you can fit any equation. And James Jeans actually complained about this, and he said there was no general relation between the masses and luminosities of the stars. And Edward Milnes, he was at Cambridge, he said that Jeans, and he wrote, just before he died, Milnes wrote a biography on Jeans's life. And he wrote that Jeans, just before Milnes died, Jeans deserves great credit for being the first critic to be skeptical about these claims of Eddington's theory, in spite of attractive plausibility which the theory was expounded. And we'll see that James Jeans' warning was appropriate when we consider the white dwarfs. Now let's look at the main sequence of the stars. So observationally, the stars of the main sequence are not revealing anything about the actual nuclear reaction which take place on their surface or in the interior. We don't know anything about their nuclear reaction. All proposals relative to stellar evolution based on changing nuclear reactions are the product of studying nuclear reactions on Earth, which may or may not exist in the stars, precisely because the stars themselves have not provided us with any information. It's improper to claim that the stars of the main sequence can only burn hydrogen. Mankind will never have at its disposal the ability to properly replicate either the internal or the surface conditions of a star. It is unwise to cripple the stars based on limited experiments and without any observational knowledge from the stars themselves. The prudent course of action is to adopt that all stars can make all elements. So the only real information that we have relative to the main sequence relates to the fact that the stars located at this position of the HR diagram share a common thermal emission mechanism. We know their spectra. That is to say, all stars on the main sequence are emitting a thermal spectrum using the same physical mechanism available to the sun. And unlike nuclear reactions, which are unknown to us, we can observe the light emitted by the stars. On Earth, thermal emission from the surface of an object is always governed by lattice type. The stars of the main sequence, precisely because they share the same ability to emit analogous thermal spectra, must share the same lattice. The only logical structure is hexagonal planar lattice, also shared by graphite and soot. So what I'm saying is that if you look at the HR diagram, the stars of the main sequence have the hexagonal lattice just like the sun, which is at the center of the main sequence. Stellar luminosity depends in large part on lattice structure. Consider diamond versus graphite, right? So graphite has a fantastic emissive characteristic, and diamonds are transparent, but they have the same density. Main sequence stars share the same structural lattice, again, hexagonal planar. Their luminosity can vary based on mass and radius, and a mass-luminosity relationship can in fact exist for the main sequence. Different structural lattices exist off the main sequence. So if you're off the main sequence, I'm saying you're going to have a different lattice. Stars of the main sequence, stars enter the main sequence as O-class objects. This is actually an old idea, but has died because now we don't believe that stars are moving down the main sequence. But what I'm saying is the stars are moving down they enter as O-class objects in the upper left, and then they slowly cool and move down the sequence as they age, provided that they can stay on the sequence and no violent or gradual change occurs. Once on the main sequence, stars only move off of it through lattice changes or exfoliative processes, such as occur in supernova or giant star formation. So I've said before, well, Wolf-Rayet stars are the first stars. And of course, the astronomers are saying, no, these are the last ones. These are the death of a star. So Wolf-Rayet stars, so we'll start with Wolf-Rayet stars because I'm going to try to argue that they're the first stars. So Wolf-Rayet stars are extremely interesting stars, and they're believed to be very massive stars, and they have 10 to 25 solar masses, but ranging up to 80. And it's interesting to note that a direct determination of Wolf-Rayet distances with stellar parallax is only possible for one single Wolf-Rayet star. I can barely read the text there. And using, which it was done with a satellite, and even that remains controversial. So what they do is they use cluster or associative memberships, which is used to provide an approximate absolute magnitude and spectral type for calibration of Wolf-Rayet stars. Okay, well, why is that? Because the stars, they have spectra that are in emission like this. They have emission lines. So Wolf-Rayet stars are characterized by the production of powerful and at times broad emission lines, which can cause an overestimate of the true continuum. Because the true luminosity is consequently difficult to estimate, they were initially classified as O-class objects. Narrower UBVR filters, not UBV filters, were specifically designed to study the Wolf-Rayet stars. So in the standard model, these are massive stars with strong stellar winds, because remember that I said earlier in the talk that if a star gets big in the gas model, it has stronger radiative forces inside of it. So they're saying that because these stars are so large, they have strong stellar winds, and which are driven by radiative pressure in their interior. These winds are thought to cause the broad emission lines, which I don't know how they would, by transferring energy into the atom and then causing the emission. So you're transferring the wind energy into the atom and causing the emission. I mean, to me, it's a little bit hocus pocus. So in this model, they are said to have a high mass loss rate of 10 to the minus 5 solar masses per year prior to dying and exploding as supernovas. So that's what they say in the gas model. So where are the Wolf-Rayet stars on the HR diagram? Well, they're not there, right? Because they don't have a photosphere. They don't have a well-defined photosphere. So you can't really assign a spectral type for them. So I just quote here, the bizarre spectra of these stars are characterized by broad, strong emission lines superimposed on a weak but hot continuum. This continuum is actually formed in the wind, and thus photospheric features are not visible in the spectra of single Wolf-Rayet stars. So they're saying, look, I mean, we have a very weak continuum, and the reason we have a weak continuum is, when we have the solar wind, now we're getting the continuum from the solar wind, and we don't see the photosphere, okay? So if you don't see the photosphere, you can't put it in the HR diagram. So in my model, what I'm saying is the weak and absent photospheric spectrum of Wolf-Rayet stars imply that their photospheric lattice is not well formed. So the stars are very hot, and you just don't have like a hexagonal planar or face-centered cubic lattice. You have condensation, and it's known that real liquids aren't good emitters, okay? So remember, when I'm saying the liquid metallic hydrogen model of the sun, I'm still invoking a lattice. I'm saying it's liquid on a macroscopic level. We see the sun is clearly got convection currents. It has to be a liquid, okay? But on a microscopic level, it must have a lattice, at least like soot, something like soot, okay? But what I'm saying in the Wolf-Rayet star, we don't even have that. They're more like a disorganized liquid without a clear lattice. So the strong and broad emission lines, so that's why we don't see a photospheric emission. So the fact that Wolf-Rayet stars don't appear on the HR diagram is telling us something very important about them, because I'm trying to say and you don't have to believe again, that the HR diagram is representing it's a manifestation of the lattice types of the stars. If you don't have a lattice, you don't appear on that diagram. The strong and broad emission lines of Wolf-Rayet stars suggest that these objects are not the site of strong stellar winds, but rather they are subject to condensation processes, which are exothermic reactions, and they result in radiative emission. So the star is actually condensing. We're actually looking at a star that's in the process of condensing. Note that the early spectra of supernova are in absorption, not in emission. So if you look at a supernova that explodes, the very first spectra that you see, the lines are in absorption. Well, if it was true that Wolf-Rayet stars are driven by powerful stellar winds, and that causes emission lines, then we surely should see the emission line initially in the supernova. But that's not true. We see absorption lines, and it's only after the supernova has exploded that now we start getting emission lines. Why? Because the material of the supernova is now again starting to condensate on itself. So now you start getting emission lines again. So hence, it is not reasonable to argue that Wolf-Rayet stars which are in emission are expelling materials through strong solar wind. The conclusion only comes from our gaseous model of the stars. So I've talked about this before. Erdl, one of the authors of this paper, is a Nobel Prize winner in chemistry, and people know here that I'm a chemist, or might know that I'm a chemist. And this is a wonderful paper where he studied silver clusters. So you could say, instead of M there, you can put a AG. So you have two silver clusters that come together to form a larger cluster in activated state, and then that larger cluster will then relax and emit. In doing so, it emits an activated silver atom, and then that silver atom will then relax by emitting light. So this is happening because in this process, in these reactions, there was no conductive paths out to get rid of the heat. So the only way that you could get rid of the heat was to emit light. So this is what I'm saying is happening in the chromosphere. To explain the emission lines that we see in the chromosphere, we're always looking at condensation reactions by small hydrogen clusters, for instance, that come together, and then you get first an activated larger cluster, and then it emits a free hydrogen, which then relaxes to give you light. And you can read the paper if you're interested. And here's another example with magnesium. I've said that the hydrides that we see in the chromosphere, the neutral hydrides, they're participating in bringing hydrogen and condensing it onto hydrogen clusters or condensed hydrogen structures. And so this is an example of that, and we see that you get magnesium plus the light. So note that in this reaction we are transferring one proton and two electrons. The same reactions can be invoked with calcium, leading to calcium-2 emissions. It is known that magnesium hydride exists both on the disk and in the sunspots of the sun. So other molecules can also be found on the sun. There's all these hydrides that can be found there, and they're all neutral. And this is the reason why the photosphere cannot be endowed with a net charge as proposed by some models. Only the corona can have a net positive charge. The solar body itself must be neutral because we have these species, these molecules that are existing right on the sunspots or right on top of the solar surface. Well, if the solar surface was charged, you would never see these free molecules. They'd be destroyed and brought into ionized state. So calcium hydride and magnesium hydride have been known to be present on the sun since the beginning of the 20th century. So we've known that these neutral atoms species have been there for a long time. So Wolf-Rayet stars, in the context of this model, the stars have a poorly formed photospheric lattice because the stars are exceedingly hot and are still in the process of actively condensing. The absence of a distinct photospheric spectrum makes it difficult, if not impossible, to classify these stars and place them on the HR diagram using standard techniques. This is because it is unclear what spectral type one should assign and how one can properly provide a luminosity for such objects. The emission lines are broad or sometimes even have unusual line shapes because they are reflecting condensation reactions and the interaction with condensed matter. We are witnessing the birth of a new star, not its death. Prior to entering the main sequence as class objects, it is reasonable that many stars first begin as Wolf-Rayet objects and progress to luminous blue variables as they begin to form a distinct hydrogen-based lattice. So then we go from the Wolf-Rayet stars to the luminous blue variables, which have a lot of similarity to the Wolf-Rayet stars. So to be clear, these are also known as S. Doradus variables, and we will talk about the instability strip later on, and I just want to make sure that you understand that these variables are of a different type. So luminous blue variables are exceedingly bright giant stars. They are closely linked to Wolf-Rayet stars. Their luminosity and stellar type can oscillate dramatically over time. For instance, Eta Carinae in the early 1800s oscillated between the 4th and 2nd magnitude. P Cygni is known to have oscillated between the 7th and 3rd magnitude. The stars are typified by violent eruptions in the context of the standard model is believed to lead to a pseudo-photosphere. The spectra at minimum luminosity have a higher apparent temperature and Wolf-Rayet-like but narrow emission lines. So that's why they're kind of similar to Wolf-Rayet stars. When they're in high luminosity, they have a very ill-defined photosphere. They have a high apparent temperature but low luminosity, and they resemble an OF/WN9 star, so they look like an O-class star. But when the stars reach maximum luminosity, they have a lower apparent temperature, about 8,000 Kelvin, and resemble a Class A or Class F supergiant with absorption lines and well-defined continuous spectrum. So luminous blue variables, in the gaseous model, the only way to account for the strange behavior of these stars is to advocate for circumstellar material, a pseudo-photosphere, mass loss rates, and instability related to core nuclear changes. But in the context of the liquid metallic solar model, luminous blue variables should be viewed as stars which are beginning to form an internal lattice structure. The process results in violent exclusionary forces within the star when the star is at its maximum, and can result in the violent ejection of matter incompatible with the lattice that's being formed. When the star is in emission, hydrogen is recondensing upon its surface. At that time, the star is much hotter and its photospheric lattice is poorly defined. Now we'll talk about a completely different type of star, and these are stars in the instability strip. So if you look at the HR diagram, there's a region of the HR diagram where the stars are very unstable. So in the standard model, take a break here. Are you guys still with me? All right. So in the standard model, so these stars have stellar instability. So you have, in the standard model, you have a gas model, and now you've got these stars, and how are you going to explain their change in luminosity? Well, what they do in the standard model is they actually change the size of the star. So in the standard model, in order to explain this, it's linked to the internal opacity of a star. As the opacity fluctuates, the star becomes more or less efficient in trapping internal light. This alters the radiation pressure, and as a result, the star is constantly expanding or contracting. In turn, this accounts for the changing luminosity of the stars. But the requirement that a star can change its physical size in order to account for luminosity changes it is associated with the need to constantly change and alter its angular momentum. So if you're doing this game where you're making the star bigger and smaller depending on its luminosity, because you have no other way. So if you look at the luminosity equation here, the only thing that you could really vary in it is r squared, right? The radius of the star. So that's why they play with it. They have no other means of changing the luminosity of the stars effectively, because the temperature can be measured. So the effective temperature can be measured. So if they can't explain the luminosity, they can only play with the radius. So they make these stars pulsate constantly. Well, to me, this is not reasonable. Okay, so what I'd like to propose is that the reason that these stars are pulsating is because they're changing their lattice constantly. So because of and you'll see in a second. So let's say if you take, for instance, graphite and you put pressure, you get a diamond structure, and these have very different emissivities, right? So in accomplishing a phase change from graphite, which is hexagonal planar, to diamond, which is diamond cubic, A carbon-based lattice changes its emissivity in the optical range from 1 to close to 0. So what am I proposing of stars in the instability strip? Well, just look at a phase diagram. My son drew this phase diagram for us. Let's pretend that we have different phases and we're sitting at some point and we're right near one of these dashed lines. So rather than argue that the stars are changing their diameters and opacity mechanisms, for instance, invoking fully dissociated helium, it is more reasonable to suggest that stars that are situated on the hydrogen phase diagram, they're situated on the hydrogen phase diagram at the interface of two crystal structures, and that they are oscillating from one emissivity to another as they alter between structural state. This has the advantage that no change in the momentum of the outer atmosphere of the stars is required versus Eddington's model, which demands a substantial periodic change in the momentum of the stars as it expands and contracts to account for luminosity changes. And I've talked about the giants before, and what I'm saying is that giants undergo stellar expansion. So in a star, you can have intercalate regions, I talked about this, and they undergo a phase change from solid or liquid to gaseous. So this transition can be gradual in forming a giant. This helps to account for the fact that G-class giants can range from dwarfs to supergiants. G-class stars can range from dwarfs to supergiants. So you have a star like our sun, and this is the bad news, the star like our sun, and if it's got intercalate atoms that it can't get rid of, it can start slowly expanding. That wouldn't be good for us. So in analogy to exfoliation of graphite, this process is not related to nuclear fuel being consumed. So all I'm asking for is when the atoms that are in the intercalate region, normally when the star is stable, these atoms should be in the solid or liquid phase. This is also true in graphite. If you have intercalate atoms, they can enter the same phase as graphite. But these intercalate atoms can actually violently expand to the gas phase, and then you get a violent explosion. And that's actually from graphite that I propose what is happening in a supernova. So in that case now, you again have in this little white circle in the star on the left, you have an intercalate region, and now these intercalate atoms undergo a phase change which is rapid from solid to liquid or gaseous, and when that happens, in an analogy to exfoliation in graphite, this process now occurring in metallic hydrogen, and it's not related to nuclear fuel being consumed. However, it can trigger new nuclear reactions because there's going to be powerful forces here, so that's why you can see nuclear reactions occur when the supernova goes. And remember that graphite itself can expand a factor of 300 during violent exfoliative processes in the laboratory. So now we come to white dwarfs. So white dwarfs are sitting at a strange place in the HR diagram. They're on the bottom left. These are quite unusual stars, and they've presented a problem for astronomy for 100 years. So here's an image of the white dwarf in the optical. And so you see Sirius B there. There's a little arrow pointing to Sirius B. That's a white dwarf. So in the optical range, it's got almost no emission. The star is like dead of emission, right? Now the other one, that's just the receiver being saturated. The star is actually not that big, okay? It's just you got so much light coming in that it makes the star look big. It's actually not that big. But if you look at the large star, that's Sirius A, and it has a temperature of about 10,000 Kelvin, an apparent magnitude of -1.5. Its mass is 2.02 that of the Sun, and it has a radius of 1.7 times the Sun. And its log of the surface gravity, so this is a log here, is 4.33. Now, if you look at Sirius B, what you see is its spectral type, it's a dwarf, it has a high temperature, it's proposed to have a high temperature of 25,000 Kelvin. It has a very low apparent magnitude. Compare Sirius A at -1.47, so the smaller the number is, so the more negative it is, the brighter the star is. And these are, again, logarithmic, so an apparent magnitude of 8.44 is very low. It has a mass now, because these stars are binary systems and they're rotating about one another, we can actually accurately measure the masses of these two stars. So we know exactly that the mass of Sirius B is 0.978. So that's it. Essentially, it has the mass of the sun. But what the gas model is saying is that the radius is the size of the Earth, 0.0084 for the radius. So we have all the mass of the sun in the size of the Earth. And they are also trying to tell us that because of that, it has an enormous surface gravity of 8.57. Now, the other thing about Sirius B is because in the gas model, this is an evolved star. Remember the white line that went through my HR diagram, from the protostar down to the main sequence, up to the giants, and then over to the white dwarfs, that because this is a white star, this is an evolved star, the white dwarf, it's considered to possess a carbon core which is surrounded by a thin hydrogen envelope. Yet the spectrum of Sirius B is dominated by hydrogen lines. And I don't even think that there are any carbon lines in that spectrum. So why did this happen? Why did we make Sirius B so small? I mean, you got to wonder sometimes. I mean, so now we got a whole star and we put it in the size of the Earth. And why did this happen? And that's because in the standard model, the only means of accounting for a change in luminosity at a given temperature is a change in the radius of the star, right? If we know the temperature and the luminosity is too low, the only thing we could do is lower the radius. So in the liquid metallic hydrogen model, however, the luminosity of the star is governed by lattice type, whereas in the main sequence stars, as I said before, share the same lattice. So here you're seeing, this is a slide that I had previously shown, I think. And you're seeing that if you have a star that is non-luminous in the standard model, you have to make R small. So this is what happened. They just said, well, okay, Sirius B must be just tiny. Okay. Because they're in a model where they have no other means of explaining it. So Eddington had concluded that stars could be treated as ideal gases, thus no other means of accounting for luminosity were possible for him beyond mass radius changes. He did not consider that emissivity in real materials is inherently linked to lattice structure. So this is what I'm trying to say, that we have to adopt what we know on Earth, that if you have a certain emissivity, it comes from a lattice. It doesn't come just from a myth. Helium accounted for the reduced That was Eddington, not helium. So he accounted for the reduced luminosity of white dwarfs by postulating a reduced radii and elevated densities given the known masses. So this led to Chandrasekhar's degeneracy, which of course was rewarded with a Nobel Prize. However, the simplest way to account for the reduced luminosity of the white dwarf is to invoke a simple change in lattice structure. Hexagonal planar on the main sequence, and then maybe something like face-centered cubic, body-centered cubic, or some other structure in the white dwarf. There's absolutely no need for elevated densities and degeneracy. Now, at the same time, it must be said that Eddington advanced that the white dwarf spectra should be characterized by strong gravitational redshifts. And these have been clearly detected in some white dwarfs. For instance, Sirius B has a redshift of minus 82 kilometers per second, and that could support his elevated densities. But the problem is that blue shifts have also been observed in white dwarf on their absorption lines, which in standard theory must now be explained by radiative levitation arguments and the presence of a circumstellar material. So when they got the redshift, they said, oh, that's showing that we have a star with a very high density. But when they had the blue shift, well, they didn't like that, so they invented circumstellar material, so material around the star where the blue shift was coming from, not from the surface of the star. So I'll just put an envelope around that whole star, and I say, well, the lines over here in this distant envelope, they're now giving us the blue shifts for the star, because we sure don't want it to be on the surface, because the surface has to give us only redshifts, because we want a gravitational redshift. So the whole thing to me is just nonsense. So unusual shifts up to plus or minus 900 kilometers per second have been reported for hydrogen alpha lines in pre-main sequence stars. So we don't say that pre-main sequence stars have these red shifts or powerful blue shifts, right? But the lines are distorted. So in the end, atom-ligand interactions are known to cause red and blue shifts in spectra in the laboratory without any requirement for elevated velocities or densities. So if you look now, this is Sirius B in the X-ray. So you see now it's much brighter than Sirius A, and as a matter of fact, it's thought that the spectrum of the brightness in Sirius A here actually comes from UV leakage into the X-ray band. So it's thought that it's really, this is NASA, that it's not actually Sirius A is not a strong emitter in the X-ray, but Sirius B definitely is. And Eddington did not know this in the 1920s, and that's an important piece of information. This demonstrates that it was improper for him to utilize the laws of emission in the optical to analyze Sirius B. This is because he did not consider all the possible degrees of freedom available to the star in emitting light. The result was that the derivation of an unreasonable radius. This eventually led to Chandrasekhar degeneracy and other even denser star systems, hyperdense neutron stars, black holes, etc. So once if you're willing to accept that Sirius B is not a condensed structure, then a highly condensed star, then that destroys any possibility to have other star species, star types that are even more condensed than white dwarfs. So white dwarfs are not carbon-based stars, but they are composed primarily of hydrogen. And this idea was also considered by August Dunning after hearing my presentation in Pittsburgh. And of course, that was a private communication. We talked over dinner about this. Now, of course, we all have our ideas in science, and August believes that we should go to Mars, and I'm sure a lot of people here believe that we should go to Mars, and humanity will decide if we should or should not go to Mars. What I want to say about it is that, because I'm in a medical school, I think we should worry about the suffering of human beings on Earth maybe before we go to Mars. But other people will decide if we go to Mars, and I'm not claiming that August doesn't have great justifications for going there, and that's a decision other people will make. But I just want to make it clear that for me, I really don't want to go to Mars. Now, I'm asking you not to laugh about it because we don't know the future of humanity. So maybe 200 years from now, people will want to go to Mars. But let's try to solve our problems here first. And just say that the three great problems for me, if mankind could come together and solve three great problems that scientists could solve, it wouldn't be in astronomy. So for me, the three great problems are the fixing of nitrogen so we could feed people, the harnessing of energy, and the desalinization of water. These are the three great problems for mankind. White dwarfs have no greater density than ordinary stars like our sun. Their reduced emissivity can easily be explained by a change in photospheric lattice structure, hexagonal planar to tetragonal. So it's just, the white dwarf is just not emitting because it doesn't have the means to do it. But notice that in the X-ray, it's a phenomenal emitter. So whatever lattice it does adopt, it's able to emit quite well with that lattice. Now, in closing, I guess I'd like to start by saying that we should love one another, okay? Don't be overcritical of people and their ideas, and try to always respect the dignity of other people, even if they have ideas contrary to yours, because nobody holds the monopoly on correctness. So I'll start with that as a first conclusion. Now, so what I'm saying is that the liquid metallic hydrogen solar model introduces an entirely new way of thinking about the sun, and this has implications for all other star types and for stellar evolution. Stars of the main sequence share a common lattice. Stars move off the main sequence when they adopt a different lattice, or when exfoliative forces in their intercalate regions causes them to undergo changes to a red giant or supernova. Stars enter the main sequence as an O-class object and slowly cool as they descend on the sequence. And while they're cooling, of course, they're making many elements. So if you look at the lower part of the main sequence, you're very rich there in molecules and elements. Emission lines, either in class O objects, luminous blue variables, or Wolf-Rayet stars, are signs of condensation reactions, not byproducts of stellar winds. We are guided here by reactions in the chromosphere and in the laboratory. White dwarfs are actually hydrogen-based stars that have different lattice structures, and that is why their emissivity is low, not because their radius is small. They are no more dense than the sun. So I'd like to acknowledge my department that's supported me these many years, and my wonderful son, Luke. And I've talked about Luke before, but anyhow, he made all my figures, and he really tries to take care of his dad. So I have a great son in my son, Luke. God bless you all.